The Giant's Causeway is a project competition we've won some time back. It's on the northern coast of Ireland. It's a beautiful landscape. It's characterized by very unique geological basalt rocks, which occur when lava flows into the ocean at a very precise temperature, which causes the crystallization of these stones themselves. Since the 17th century, because of its easy access, it has actually been a tourist destination for as long as for over 300 years, posted from the past. The visitor center is actually for two sets of program. One, which is the visitor center, and the other, most importantly, is actually the car park. It's situated on the lower left-hand on the bottom edge at the tip on the other side of the cliff face. The project is effectively two steps in the landscape, one going up on the left-hand side, one going down on the right-hand side, left accommodating the visitor center, right the car park of over 350 cars. Here you can see the two cuts. One goes up for the visitor, down for the car park, revealing the striations of the basalt column and the structure. And the stone itself. The materiality of stone is actually quite interesting. For lack of a better word, it's a highly contingent structural nature of the stone. It has actually six sides to it, and the reason you never see a basalt column standing on its own, it actually relies on two of the sides touching another stone column in order to gain its support. Hence the fact that you only see them in a topography and never as a single column, because they will never hold up by themselves. Organization of subdividing on the left-hand side is the visitor center. You can actually see the car park is about 6 to 7 times the size of the visitor center. So even though the building was important, because of the size of the car park, it actually presented itself in terms of a need to address its architectural legibility. So therefore, the one thing that cannot change in order to subdivide the site is actually the grid of the car park radius, which is the car parking system. It's based on a 6666 meter module, which is car parking, two-way drive-out car parking. In order to accommodate the stone facade, we had to further subdivide the car parking into a smaller number in order to accommodate the size of extraction of the stone. Here you can see the random nature of the basalt columns. So the basalt. Part of the sustainability agenda is not to import the stone from China at half the price, but to actually use local basalt. And unfortunately, given the local basalt, it actually, given its properties, can be ground up, and for all intents and purposes is only used for roads. So how do we deal with the weak capacity of this stone? Further testing was actually done prior to tender. We drove rods into it. We broke up stones to determine the waste ratio, which is a ratio of 1 to 4. For every one stone extracted, 4 would be wasted. This shows the compressive and flexural strength of the stone. The other two, the top one, 275 MPa, very strong, close to granite. Flexural strength, extremely weak, 5 to 15. But what's interesting about this is actually not the strength of the stone, is the fact that the line is not straight, which means the extraction of the stone is unpredictable. And how do we build this unpredictability into the overall tender process of design? So this means the stone must be used in compression, which is the old Parthenon method. On the left-hand side, you see a Doric column. The great thing about a Doric column, it has a 5-to-1 ratio, and the dead load of the column is extremely heavy, which means you can't push over something which is fat and wide. However, given the nature of basalt, it is very small, and we don't have the dead load of the stone, so it becomes very flimsy. How do we actually bring that back into compression? So the stones are actually stacked. So you start with the bottom, a steel plate, you stack them on top, and you actually string them together with a series of tension rods, and the tension rods would simulate the compressive load on a relative nature that the individual columns would actually perform for wind loads similar to that of a Doric column, effectively using the high technology to actually simulate its needed dead load to resist the overturning load on the columns themselves. On the left-hand side, it shows the extraction of the stone. We have 600 stone, 450 stone, and 150. And lo and behold, the extraction process didn't yield the 4-to-1 ratio, which we actually did. However, we built that into the construction process. So when the yield of the large stone actually begins to go down, the subdivisions within the columns begin to shift based on a system. And effectively, what ends up happening is that the facade of the building becomes a registry of the extraction of the stone from the quarry. So if you're walking along column line A, you would say, oh, that's July. That was a good extraction day. We got rid of very large boulders. Go to column line B, we see that was a really bad month. The stone was very small. The number of subdivisions actually decreased. So as you walk along the facade itself, you can track 6 months of extraction in terms of the sizes of stone and the sizes throughout the whole period. A construction process, you can see here the elements. The central one is the alignment dowel. The two sides are actually the tension rods that go through it. The plate, the tension rod, the stacking of the stone, and the final capping of the stone. Here you can actually see the subdivision of the system. The subdivision is actually a realignment of the angles. So there's a series of 3 angles. The widths of the stone are all the same, but by twisting the angles, you actually produce different sizes for the stone. Sorry, different shapes for the stone, but all the same width, and variations of subtraction addition to create the random pattern. So the steel columns, in order to acknowledge the shift, rather than using just this rectilinear column and rotating it, we bifurcated the column into a series of 25 mil steel plates, shifted them by 37.5 degrees in the vertical direction, which allowed us to create the angular nature of the grid by actually using an orthogonal system to actually show this nature. This is the bolting together of the columns, and you can actually see the view of the columns center and the shift in the plates that support the roof above. And the last thing, not only did we have a weak stone, we actually had a weak balustrade, given the geometry of the building. On the left-hand side, the 3 kilonewton load that needed to be sustained, but you can actually see the loading of the balustrade is at an acute angle. Normally, for 3 kilonewtons, you want to resist the exact same amount in the 3 kilonewtons in the perpendicular direction, most efficient. Unfortunately, it puts our orientation puts the steel along the long side of the triangle, which means there's 40% more steel, 75,000. How do we deal with this without increasing the cost of the project? We need to just pull it back and resolve the overall triangle in the plane of the facade, and we achieve this by adding 2 simple rods to actually complete the triangle. So within each field, which is the length of a truck, we simply just add 2 steel rods, and that's the project.